coming to the automation, you know that automation computer or microcontroller functions as controller where the inputs are machine codes. And also, when you compare the accuracy, so accuracy of digital signals are more. How it is, the digital signals are represented in terms of zeros and ones. Usually, typically, number 12 bits again, 12 bits or more to represent a single number. So this involves a very small error as compared to the analog signal. The analog signal very disadvantage is the noise and power supply drift. Analog signal analog signal. Sorry. So here, that is the way accuracy of digital control systems are more comparing with the analog control system. Then coming to the implementation error. Implementation error and the processing, the errors digital negligible. The processing of control signals in digital processing is done in digital control. So that is, it involves addition, multiplication by the already stored values in addition, multiplication. So the errors that result from digital representation and are always negligible. But the processing of analog signals is performed using components such as resistors and capacitors, like resistor and capacitor, with actual values that usually resistors and capacitors, usually a tolerance will be given by the manufacturer, plus or minus 1% or 5% or so. So, and if we measure the resistor value in a multimeter, you may get it for a 1 kilo ohm. 1 kilo ohm, it has to be exactly 1000 ohm. You will not get exactly 1000 ohm. It may be varying from 950 ohm to 1050 ohm. So that creates a problem while designing the analog controllers. So comparing with the digital controllers. Okay. So the passive elements will create a problem. Due to that, the implementation errors are more in analog comparing with digital. And flexibility. Flexibility is flexible. Modification of a digital controller is possible. It is flexible without complete replacement. Whereas analog controller is difficult to modify or redesign. Once already PCB is already the redesign digital controller implemented in firmware or software. Software is modification. A line, codes line the controller is modified. The design is modified. So the digital controller modification is possible without a complete replacement of the original controller, as we are doing in the analog controller. So that is the flexible nature of digital control. And coming to the speed of the computer hardware increase gigabits per second. So the increase in processing speed has made the digital controller to do sample and processing in a very speedy manner, in the sense if the delay will be of the order of nanoseconds. So, or even if we are using the digital controller, the continuous monitoring of the control variable is obtained, whereas in analog that is not obtained also. So then coming to the cost, you can see that the digital controller are more economical. In the sense, usually we can say that in the digital control there is an added block of ADC and DAC comes. Then also the prices of the prices, like it is the area and the cost using VLSI. You can see that the very large scale integration is possible now. That technology is used so that the cost can be reduced by increasing the speed or decreasing the area of etc. The controller cost can be reduced. Then I am giving a structure of digital control. Structure of digital control in the sense here I have given analog control. Just to this already we have discussed. In the classroom, So analog controller already you know. What are the added things that comes in digital controller is the ADC and DSC. That is the to control the physical system or process using the digital controller, the controller must receive measurements from the system. So here we can see that almost all applications, the plant, here the plant or process, the actuator and the process, this is actually the plant in industrial terms or the control engineers terms. So the plant and the actuator and the process are analog systems. It's a real time, it is analog. But so what happens? The controller output, that is, the controller and the process variable do not speak the same language. So there is a need for translation. The controller or the computer is recognizing only the machine codes, whereas the plant or the actuate plant and the process is recognizing only the real time value, in the sense only the analog values. The plant output, output, the controlled variable, this output or the sensor is also analog. So these two can recognize only the analog or the continuously varying time function only. If it is a temperature, what is the time now? You will not say a binary value. You will say it is 10:30 or something like that. So similarly, the actual happening in the world is real time and it is analog. So the analog output is to be processed in digital. That is what we have here. We are doing in digital control. So the controller and the process should speak the same language, meaning should speak the same language in the sense, if it is the computer understands only machine codes, that is binary only, that means only digital values, then make the sensor output also digital. So for that we are using analog to digital converter in the feedback part. And again, the computer sends the commands in machine code, again, that the binary. Then, but that machine code is not understood by our plant or the process. So that is to be converted back to analog for getting the process to be controlled. So that is what here it is done. That is the translation from the controller language, that is digital, to the physical process language, that is analog, is performed here in digital controller. For that, these two blocks, the analog to digital converter and the digital to analog controller, are used. And a sensor, also a sensor, you know that the sensor is analog sensor only we are using. So the analog sensor output is converted to digital for the computer or the processor, or nowadays it can be smartphone also, to do the control action. So this is structure of a basic digital control system. This one is the block diagram representation of a digital control system. This is for the analog control system. This I have given analog control, and this is digital control. Okay. Then some examples, daily life examples I have shown. This is the example of a drug control system, close to drug delivery system. Drug in the sense it is the medicine or the nutrients. Okay. So we can see that, say for example, the chronic diseases require the regulation of patients' blood levels. For example, some diseases like failure of the body's natural closed-loop control of blood levels of nutrients is results. So most prominent these diseases, the diabetes, where the production of hormone insulin that controls the blood glucose level is similar. So here the blood sensor, here it is actually the for example, we can say the blood sensor can be in general. So here if the blood sensor is sensing the sugar level of the blood, you say that blood glucose level. So to design like this closed loop drug delivery system, in addition to the sensor, you should have a system for the controlling, isn't it? This blood sensor will sense the glucose level only. So that is detected, that is converted to, here you can see that the block diagram shows it is blood glucose level will be a log value. That analog value will be converted to digital, as I said earlier, and it is fed to the system, PC or the laptop or the smartphone, whatever it is, and the it will be compared. So here we can see that this is there, and inside this is comparison is done with the actual value. So already the required value is fed here as a command, and the actual value is obtained. The computer is doing the comparison as well as the controlling. So comparing, and if that is less than the required value, the drug pump, in the sense the glucose uh, glucose level pump button, like, you can see that is like this, the with the knob here. So that bottle, that valve will be opened such that the patient will get that glucose through the, like, through using a simple trip arrangement. That's trip, giving a trip to the patient. The trip will have, that is actually nowadays we are the nurse may control, but in big countries or in sophisticated hospitals, this is done automatically. So if it is required, then only the glucose will be, or insulin will be injected in. Otherwise, it will not. That is done automatically using the um, digital control. Okay. So another example is the aircraft turbojet engine. So this is also it is having the aircraft turbojet engine is having three. It is actually as a multi input, MIMO, you will say, multi input multi output digital control. You can see that there are two or three inputs are coming. So sensing is done in two stages. So here engine condition is sensed here, and the aircraft is also sensed. So the aircraft state, that is, what is the state of the aircraft, in the sense what is the altitude of the aircraft. So here the control requires feedback of the engine state, that is speed, temperature, and the pressure, and the measurements of the aircraft state, the direction, as well as the altitude, and the pilot command from the aircraft. So these are compared and controlled inside a room in a system or a laptop. So this is another example for a MIMO digital control system. Of course, it is feedback of the closed loop control system. So I think it is. Now this is an example that shows that I have already shown you that with the animation, that is the automatic water level control. So can you see? I have to share, I think. So this is just an animated of the automatic water level control. You can see that lever and pivot arrangement, how it is. Can you see that? Hello?
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
Yeah. This is simply an animation that is I have taken from Google only. It is just showing the animation. You can see that water is when the water level is below normal. Below normal means empty. The water flows in. How it is using this lever and pivot arrangement. The valve inlet valve closes when it becomes full. That is, this is the float, as I have shown as blue color. Float will be floating in the water. It is not immersed. So that is the theory behind that. And this lever and pinion arrangement. Okay, the pinion will close the inlet valve that you can see here. Here you can see. This is the inside of this is shown here. Is that okay?
Yes, ma'am.
So I think we will stop now. Actually, I'm waiting for the prerequisite, because now after that we will go on to the sampling. Sampling, how sampling is done in digital control. So you should know what is sampling. Some numerical sampling theorem that you work out. You will be just go back and review